Hi, my name is Krishna Kumar Narayanan, and I'm going to present my project, Credit Card Fraud Detection. It is done for the Coursera course IBM Advanced Data Science Capstone project. Okay, so credit card fraud detection. I would start off right away with the problem definition. The problem definition is such that we are provided with a data set full of credit card transactions which are either labeled as fraudulent or normal transactions. And the task here is to detect fraudulent credit card transactions from the data set. For that, we develop a classifier to identify the fraudulent transactions. Important here is to note the data set is imbalanced data set in that we have only 0.172% of the entire samples labeled as fraudulent. And the data set is recorded over 2 days in September 2013. And the data source is from Worldline and Machine Learning Group of University of Brussels in Belgium, and they have made it available in Kaggle. Important to note here is one of the main tasks is to reduce the type 2 error in that our model should make less type 2 errors as possible, in that a wrong classification of a fraudulent transaction must be penalized heavily than a wrong classification of a normal transaction. So the contents of my presentation is going to be as such. I want to start with the data set, followed by my architectural choices. Then I will explain the data exploration and transformation phases, followed by the performance metrics that I used, and then the different modeling algorithms used and their evaluation, followed by a short summary. So like I mentioned in the first slide, we have an imbalanced data set, and this can be seen on the table to the right, where we have almost 280,000 non-fraudulent normal transactions and just 492 fraudulent transactions. The features that were provided to us were totaling to 31, and this included a time column, which is the time elapsed in seconds since the first transaction of the data set, and followed by 28 PCA features. The providers gave us only the PCA features and not the original features due to confidentiality issues. Followed by another column or another feature, which is the transaction amount. The labels were then classified or just labeled as 0 and 1 for non-fraudulent and 1 for fraudulent. What are the architectural choices that I made? The whole project is done in Python. And in Python for data handling, I used pandas, numpy, and IMBlearn. IMBlearn is the module for imbalanced data set handling. Matplotlib and Seaborn for data visualization, followed by for the machine learning module, used sklearn, which is the scikit module, and Keras with Tensor for backend for deep learning issues. As a development environment, I used the IBM Watson Studio Jupyter notebooks. For local development, I used PyCharm IDE. The data storage of all the model performance metrics as well as the data is in IBM Object Store. So this helps in loading my Jupyter notebook anytime, and thereby have a repeatability and reliance of my results. Let's go to the data exploration. Data exploration first, what we do is do the so-called feature distribution of the individual PCA components. And as we could see, since the features are already as our principal components, they had to be standardized in its original format. And this could be seen with the feature distribution, where most of the features have zero or close to zero mean. Nevertheless, some of the features exhibit high skew and kurtosis. Skewness here is the asymmetry of the distribution of the individual features, and kurtosis is then the tail of the distribution, how long, how short the tail is. So this follows up with this is followed up with the statistical moments of the individual features, and this is quite clearly evident in the plot, where we could see the standard deviation reducing by through the features. And this is understandable because the feature sets are individual features are PCA components, and the PCA components have the property that they The first big principal component represents the highest variation in the data set, followed by the next principal component, and so on. And it is only understandable that the standard deviation is reducing over the time over the number of features, and the skewness and the kurtosis plots also show that there are some features which have very high skewness nature and have a long tail with respect to kurtosis. As the next step, we did cross-correlation. The cross-correlation shows that all these individual PCA components are extremely independent, so there is no high cross-correlation. Some features show some cross-correlation with the amount, or the transaction amount, where we have V2 and V5, V6, for example, V7 have a cross-correlation of 0.5, 0.3, and 0.4. Nevertheless, since we don't know the intuition behind the original features, we cannot just tell why it's the case. From the cross correlation, we could see that we don't need to remove any features because of any high correlation problems. Just to give you an insight as to how the features look like, here's the feature scatter between two components, V1 and V2, and as well as V1 and V3. And yeah, one could say that the fraud and the non-fraudulent features have a quite clear trend. Nevertheless, there is a lot of features which overlap there is a huge overlap between the non-fraud and the fraudulent features, as we could see here and here. So data transformation, as a part of the data transformation, I first look for the invalid values and not a number values and replace them with 0. Check for duplicate entries, remove them. Standardize the features time and amount, and I gave new feature column name scaled time and scaled amount. So our data is an imbalanced data set, like I mentioned before. So before we start balancing out the data, I split the data using a 70-30 holdout cross-validation, where 70% of the data is used for training and 30% for testing. And I created a balanced data set from the training data set using the following techniques, which are random undersampling of non-fraudulent samples, random oversampling of fraudulent samples, or the SMOT oversampling, which stands for synthetic minority oversampling technique. Random sampling is in random sampling we just randomly sample the data with or without replacement, depending if it's an oversampling or undersampling. No new data points are generated, just more samples of the existing data are created. For example, for undersampling, we randomly eliminate points from the majority non-fraudulent class, which is shown here to the right side, where the distribution between V1 and V2 for an oversampling looks exactly like the distribution of the original data set. Similarly, undersampling plot is shown to the left. SMOT oversampling is a little different to random undersampling in that it creates new samples of fraudulent classes by interpolating between randomly selected samples in its neighborhood. For example, it selects a sample A from the minority class, and then it looks for its k nearest neighbors, and from its k nearest neighbor selects another sample B, and then interpolates between these 2 points A and B. What are the performance indicators that we used? For this imbalance problem, I used area under the curve, AUC, as one performance metric, followed by the type 2 performance metric, which is the specificity, which tells us the proportion of the actual fraudulent cases correctly identified, also sometimes called as the true negative rate. And also finally the harmonic mean of precision and recall, which is reflected by the F1 score. So for a random prediction, the F1 score is 0. For a perfect precision and recall, the F1 score is 1. What are the modeling algorithms used? I used the following approaches. I started off with support vector machines on the undersampled data set. I did it once with the backward chaining feature selection and once without feature selection for a comparison. And then I did random forest ensemble algorithm with all the 4 data sets, followed by a deep learning approach with a fully connected neural network, and I used the random oversampled and smooth oversampled data set. And finally, in order to check the performance of how the data set would work under with an autoencoder for anomaly detection, I did a trial run of that as well. Here the model evaluation. So first we see the results of support vector machines with feature selection, and one could see here bottom that we have an area under the curve of 0.97, which is pretty good on the test data set, the results, and it has an F1 score of 0.115. This is not so good because we expect a much higher value, and this is because many not fraudulent data sets, around 1900, were wrongly classified as fraudulent. These are the sensitivity rate is quite high, but the specificity is 0.93, where we make only 9 mistakes out of 136. But when we do without the feature selection, the results are marginally better, but quite similar in that we have an improvement in F1 score of 0.24. We make less sensitivity errors, but the specificity rate remains the same. Then I did the ensemble method for random forest on all the 4 different data sets, and from the results one you could see that the best performing one is the one trained over the smooth oversampling data set, where we have a AUC score of 0.98 but an F1 score of 0.85. This is a considerable improvement to the support vector machine methodic, and we also have a very high specificity of 0.86. Finally, with the deep learning approach, I used fully connected network. I had 2 layers, one with 64 nodes, second layer with 32 nodes, finally, 3 layers, and the third one with 16. And with over a sigmoid activation, then do the prediction of one value, which are the classes. I used the optimizer Adam, learning rate of 0.001. 50 epochs, the loss binary cross entropy, batch size of 256, and use the oversampled and the original dataset. Results show that all the 3 data models perform quite similar, in that the specificity is the highest for the smooth oversampling dataset. The improvements that we can achieve is by doing a class weighting. I already did a class weighting here, where I weighted the fraudulent data sets higher than non-fraudulent, and here there is a potential improvement where we could do a grid search over the class weights to improve the performance. More hyperparameter tuning, and if he have more data availability, the model performance can be extremely improved in this case. Here is the results shown for the smooth oversampling dataset. Finally, to complete, I did an anomaly detection using KRAS. So I have the encoder and the decoder summary here. The encoder has 64 nodes in the first layer, followed by 32 to an encoding code of 16. And the decoder takes the 16-dimensional vector as input through 32 node layer, followed by 64 node layer, to give out output which is 30, which is exactly like the input features. And as the loss, I used mean squared error, and the training data is then only performed on non-fraudulent examples because the anomalies are the fraudulent examples and we want to test it. The evaluation is done on both fraudulent and non-fraudulent samples. The results show that the precision recall curve for the test data set, that the threshold lies somewhere around 25, and the results show that we achieve relatively okay results, but not necessarily as good results to the one for the supervised learning. Nevertheless, there is some potential here, and by doing more hyperparameter on different networks and different codings, embeddings, there is quite a potential in autoencoder evaluation, but this was just a proof of concept curiosity to see how it would perform for an anomaly detection. Finally, the comparison of all the different models show that the best performing model in our case is the random forest trained over smooth oversampled dataset. So in summary, what we performed was give a problem description. What we did was give a problem description of the project, followed by data exploration and transformation. And then I addressed the problem of imbalanced data set and how did we balance the data using random over and undersampling, followed by a smooth oversampling. And the model building was done with support vector machines, random forest, fully connected deep learning, and autoencoder based anomaly detection. And these results were compared, and phases of improvement, what changes were addressed, and thereby a better performance was achieved. Yeah, that's the end of my presentation, and thank you very much.